Hi guys, I would like to try to do this quickly. This is a really cool equation I want you guys to know conceptually and mathematically, but mainly conceptually. So really focus on the concept for this one. For flow rate, the proportion math is really important. So what you want to remember is that the velocity is determined by the area only. That comes first. Okay? It does not matter if it's going uphill, downhill. It does not matter the orientation of your pipe. If you're assuming an incompressible fluid, the flow rate is constant, therefore area times velocity must stay constant, therefore the velocity is determined by the area only. So that which I just said, you guys should be able to vocalize boom, 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 boom in order. So if that's the case, and if I have a fluid flowing through a pipe, then we can start to take into account other variables and ask ourselves what happens. So if this is a height h1 and this is a height h2, by the way, the height is measured to the center of the pipe, and I have a velocity or a flow speed v1 here, a flow speed v2 here, that is determined by the area a1 and a2, which I'm not going to mark. And since we're in a pressure, since we're in a fluid, we have a pressure P1 here and a pressure P2 here. Bernoulli's equation relates these three. How does it do it? Well, it says that as something flows, as a fluid flows, energy is conserved. Which means that the energy at point 1 equals the energy at point 2. So, in a nutshell, oversimplified, this is Bernoulli's equation. Sort of. Right? We want to write it in more detail, but this is where it starts. So you want to remember it starts here. You always memorize the end, though I want you to know the end. The end is the most important, but I also think it's partially important, more than zero importance, to remember where it comes from. So, what are the different forms of energy? Well, we have kinetic energy. What else do we have? Potential energy. And we have the work done by the fluid on itself, right? So we have work done, so the energy added or taken away by forces. That's going to equal the kinetic energy plus the potential energy plus the work at any other point here. So this is now the extended version of Bernoulli's in its raw form. Let's plug in the formulas. So kinetic energy is 1/2 mv1 squared. Potential energy is mgh1. So work, just in its main form. And we're going to write the same for point 2. Remember, we're dealing with a fluid. And since we're dealing with a fluid is described by its density. Density is mass over volume, so we want to divide everything by volume, and since we have to divide one thing by volume, we have to do it, of course, because of math, to everything, so that the equation stays balanced. So the mass over volume becomes 1/2 rho v1 squared plus rho gh1 plus work over volume equals 1/2 rho v2 squared plus rho gh2 plus work 2 over volume. So here's the almost end of Bernoulli's equation. I'm going to do a little aside here. This is really cool, guys. If I have a cylinder of a fluid and I apply a force F, and it has some area A and some distance D. And what is the work done on the fluid? Well, the work is the force times the distance. Right? But if we divide by volume, then volume is area times distance. So the work over the volume, just from a simple geometric argument, is the same as the force distribution over the area. What is force over area? So this is the most important part about Bernoulli's equation, guys. This is it. So pay attention to this concept that the pressure of a fluid is the internal work that the fluid does on itself per unit volume. So what pressure is it's the internal work that a fluid does on itself per unit volume. So pressure is energy density. So remember, if we divide by volume, these are technically kinetic energy density, potential energy density, work density, kinetic density, potential density, work density. So technically, Bernoulli's equation is energy over volume equals energy over volume. Energy density stays constant. That's not that important, kind of. Why that's important is that the pressure itself is now another form of energy. So why does that make sense? It should make sense because any point here is going to have trillions of molecules exerting forces on it from behind, which is going to do work on the fluid. So if you have another point here, tons of force vectors pushing on it, but also tons of force vectors pushing back this way too. Remember, pressure pushes from all directions. So if we have a pressure differential from P1 to P2, that's how we get that force vector from one to another. So let me emphasize. Pressure is now another form of energy. The pressure is the fluid pushing on itself. It's a force of the fluid on itself, and therefore it's a source of energy for itself. So now there's another source of energy that is not just kinetic and potential. So here's Bernoulli's equation in its raw, completed form. That's the one you want to know, but I care more about the concept. So let's talk about that. So what's the concept of Bernoulli? So let's write it out. So remember, kinetic, potential, pressure. Pressure is now a new form of energy. It's another form of fluid energy, internal energy the fluid gives itself. Stop and think about that for a second. That should actually make some sense because pressure is force over area, and all those little trillions of molecules behind one molecule of water are going to push on it, right? So a single molecule experiences, it's not alone. It's not a free body diagram. It's definitely not a free body. It's experiencing, well, it's free in the sense you can isolate it and talk about it in terms of forces, but it's not an isolated unit flowing on its own. It's being pushed by tons and tons of things behind it. So what does this say? Well, let's do an example. Our previous problem said that, or our previous flow rate video said that fluid flowing uphill, say it flows up 5 meters. If we have the same cross-sectional area as we do here, then we have the exact same velocity as we do here. So then what's changed? And what is the upward force now that is going to counter gravity that's trying to keep the fluid down? Because if we have a constant velocity, Newton's law says that constant velocity means no net force. So what we end up getting is that the pressure at point 2 has to be less than the pressure at point 1, because if we have more pressure in some point and I have less pressure in some point, we have a force vector from more to less pressure, because the more pressure is pushing more than the less pressure, so we have a force vector that way. So we get a force vector up from the pressure differential that counters gravity. So P2 is less than P1. Here's how you look at it. If H2 increases, this is the same, so it cancels. H2 is larger. To balance the equation, think about it for a second. This goes up, this has to go down. So if height increases, pressure decreases. And if height decreases, pressure increases. So this is Bernoulli's effect, part 1. Stay tuned to part 2.